Hello everyone, this is my micro learning environment design for ED403. I will be looking at a course that I am teaching, EE321 Power System Analysis by Hadi Sadat. We will be looking at just a particular part of it, which is power factor correction. This comes under course learning outcome 1, which is to analyze simple interconnected power system in normal and faulty conditions. The lesson plan for this micro LED is that firstly we have a small introduction with theory, then we'll solve a example question using Matlab, then we'll have a quiz at the end of the session. Power factor correction. What is the problem? Taking in consideration the power formula P equals to VI cos theta, the apparent power will be larger than P if the power factor is less than 1. Thus, the current I must be supplied will be larger for Pf less than 1 than it would be for Pf equal to 1. Even though the average power P supplied is same in either case, a larger current cannot be supplied without additional cost to the utility company. Thus, it is in the power company's and its customers' best interest that major loads on the system have power factors as close to 1 as possible. Now the solution to power factor correction is, in order to maintain the power factor close to unity, that is 1, power companies install banks of capacitors throughout the network as needed. In some cases, additional charges are also imposed to industries who operate at lower power factors. Since industrial loads are inductive and have low lagging power factors, it is beneficial to install capacitors to improve the power factor. Some formulas that you need to remember while doing problems of power factor corrections are that the complex power is equals to VI conjugate, which is also equals to the real power plus JQ, the reactive power. Power factor is equals to cos theta. Reactive power is equals to P tangent theta. Reactance C is equals to V squared divided by S conjugate. And finally, the capacitance is equals to 1 over 2 pi f, which is the frequency, times Zc. All these formulas can be found out from the power triangle shown in the figure below. Now let's look at an example and do analysis using Matlab. So I may open Matlab here. Okay. So first thing that we are going to do is note down all the information that is given. So we are given L1 is equals to 100 plus 0j. L2 is equals to 10 plus 20j. Supply voltage is equals to 200 plus 0j. Okay, and the frequency given is 60 hertz. Now remember that V is equals to IR. So I1 will be Vs, which we have already defined, divided by L1, and I2 will be Vs divided by L2. Now we are going to find the apparent power. We know that S is equals to Vi conjugate. So S1 will be equals to Vs times conjugate of I1. S2 will be equals to Vs times conjugate of I2. Now we know the apparent power. We can find the total apparent power. So the total apparent power is S equals to S1 plus S2. Remember, S1 is the power flowing through the 100 ohms resistor, and S2 is the power flowing through the 110 ohms and 20 ohms inductor. So we have our total apparent power. Now we can find the total current. So that's I is equals to conjugate of S, the total power, divided by the conjugate of PS, supply voltage. Okay. Yes. Now we can understand what is our power factor. So power factor at source is equals to PF. We are going to say PF equals to cos angle of the current I. Okay. So let's see what our initial power factor is. If we run this, we should get our power factor, initial power factor. Okay, the initial power factor is 0.6. So it says find the total real and reactive power. We have found that, and find the power factor at the source and the total current. Now the next thing is we want to improve this power factor to say 0.8. So we want our new power factor PF to be 0.8. Okay, how can we do that? So let's define theta 1 to be equal to cos inverse. So that is a cos in Matlab 0.8. Now the reactive power will be real of S times tangent theta 1. Okay. Now the reactive power that needs to be consumed by the capacitor, so we are going to say QC is equals to the imaginary part of S, the total power, minus Q that we have computed in the previous line. So let's see. So 700 kilowatt of energy needs to be consumed by the capacitor. So what is the size of the capacitor that we need? First we have to find ZC, which is equals to source voltage squared divided by QC. Okay. So once we know our ZC, we will be able to find our C, which is equals to 1 divided by 2 times pi times F times ZC. So let's see what is the size of the capacitor needed. We need a 46.42 microfarad capacitor bank. to improve our power factor from the initial power factor was 0.6 to the new power factor which is 0.8. So remember that when the power factor changes, the amount of current observed or supplied will also change. So let's see what is the total power and new current. So S1 is equals to real of S plus Q times J, and I1, then I1, the new current, will be equals to conjugate of S1 divided by conjugate of Vs. Now if you want to see the current difference, we're just going to put it in a matrix form. So ABS I, sorry, ABS and absolute of I1. So you see, previously at power factor equals to 0.6, the current being supplied was 10, and now with the new power factor, the corrected power factor from 0.6 to 0.8, we get a current consumption of 7.5 amps. So now you see the importance of power factor correction. Now let's move on. So this is um, a program that you can use for any question which is power factor correction. So you have a quiz now. You can use the same program to solve this quiz. Thank you very much. The reference is from Sadat Power System Analysis.